today we have another contributing speaker session. It will be quantum neural network. It will be focused on quantum neural networks, and we start with Yadong from Tsinghua University, who will tell us about their scrambling ability. So the floor is yours, Yadong.
Okay, thanks, Anna. And hi, good morning or good afternoon, everyone. I'm Yadong Wu from Beijing. And today I'll talk, thank the organizers give me the opportunity to introduce our work. And today I'll talk about the scrambling ability of quantum neural networks and build the connection to the machine learning efficiency. Okay, so first, suppose we are all familiar with the deep learning and classical neural networks. For the supervised learning tasks, the deep learning and the neural networks have been very successful at many aspects, such as the pattern recognition or optimal controlling. So for here, we consider the supervised learning tasks and consider this very simple example. We can use the machine learning model to classify two different kinds of images, such as cats or dogs, which are very high dimensional vectors. Using the machine learning model or the neural networks, we can optimize the parameters of this machine learning model, and the prediction of these neural networks can be very close to the label. So this machine learning can give us a very high accuracy. Basically, the supervised learning is that the neural networks can extract the information from a very high dimensional vectors or the matrices and encode the information to a low dimensional output. The target is to optimize the parameters in the neural network, such as the W or the bias B, to make the output as close to the label as possible. And in recent years, people focus more about the quantum system and like the quantum information, quantum computation, and generate the quantum neural networks, which can be used to deal with the quantum wave function and to give us a good prediction about the physical properties like the magnetization or the correlation functions. Generally, this is the simple structure of the quantum neural network, where the psi is a wave function as the input of this quantum neural network. And this structure is also similar as a classical neural network, which is built layer by layer. And after this set of unitary transformation, we can do the measurement of the output. And here we can obtain the measurement to make it as close to the label as possible. And then let's compare the classical neural network and the quantum neural network. The one element of the classical neural network is the nonlinear activation function. There are three popular activation functions, such as the rectified linear unit function, the logistic sigmoid, or the hypertangent. Because of this, and the derivative of this nonlinear activation function has a very simple analytical form. So for this nonlinear activation function and the repeated layer structure, the classical neural networks have the universal approximation theorem, which means that a neural network can be used to fit it as close to a continuous function as possible with any high accuracy. Just take a very large or very deep classical neural network. However, because of the nonlinear activation function, it's very hard for us to recover the input data from the output of this classical neural network. So we call the classical neural network is information lost. While for this quantum neural network, because all the transformation of the input wave function are unitary, which means are all linear transformation. So here, by the way, here we don't consider the measurement. So we can do another linear transformation to the output wave function and apply the set of unitary, and we can recover the input wave function again. So in this way, we call the quantum neural network is information preserved. Okay, and here we consider more specifically, we consider this kind of quantum neural network structure. The input wave functions sent to this quantum neural network, and after a set of unitary evolution, we take the single qubit measurement of the output function. Here is the measurement operator, where for the readout qubit is the Pauli sigma x, and for the other qubits are all identity. So after the evaluation of this quantum neural network, the wave function is a U psi. And the Y tilde, the output of this quantum neural network after measurement, is the expectation of this operator. So from the left to right is also the neural network is also extract the information from the high dimensional quantum wave function and encode the information to a low dimensional output. The target so we can use it to solve the kind of machine learning problem where the target is to optimize the parameters in this unitary to make the measurement of the output wave function as close to the label as possible. And we can also regard this process in in another way. So first, we can also encode the information to the single qubit, and because this quantum neural network is information preserved, so we can apply a set of unitary transformation to scramble the information which encoded at the single qubit to the entire system. So from the right to the left side is an information scrambling process. And now here we build the connection between the machine learning and the information scrambling. For this quantum neural network structure, we know that different structures, the information scrambling ability is also different. Let's see these two extreme examples. For the left structure, we can see for the left structure, each unitary just applied at every single qubit. There is no coupling between any two qubits. So while the information encoded at the single qubit, it's impossible to scramble this information to the entire system. And the information scrambling ability of this quantum neural network is very worse. And for the right quantum neural network structure, this large unitary operator coupled the entire system. So while we choose the suitable parameters of this unitary, the information which encoded at the output or at the single qubit can be scrambled at the entire system. So for a specific quantum neural network, there are two properties. One is choose the suitable structure, and the other is the suitable parameters. But for the machine learning tasks, the parameters of the neural network can always be optimized by the data. So while for the structures which are fixed before training, so we want to find out what kinds of quantum neural network structures is better. Before we answer that question, we ask another question. So what's the meaning of better? For the machine learning side, we can use loss function or accuracy to characterize how good a quantum neural network structure is. But these quantities are always can be known after training. But for the information scrambling side, we can use tripartite information or operator size growth to characterize an operator how complicated or how entangled about the system. And these properties are prior information and which depend on the quantum neural network structure. So here we use the operator size growth to characterize the information scramblability of a quantum neural network structure. Here, first, let's see what the single qubit operator in Heisenberg picture. At the beginning, it just applies to a single qubit, but with the time evolution, these commutators become more and more important. So this operator can couple to another qubit, and finally, the entire system can be entangled together. Generally, an operator can be expanded by a polystring basis. For each qubit, this operator have four choices: the identity, sigma x, sigma y, or sigma z. And we can use the operator size to characterize this how complicated this operator is. Here, the L is the number of this polystring contains the operator which is not the identity. For example, for the single regular qubit measurement operator, just the regular qubit is a polysigma x, and for the others are all identity. So for this operator, L equals to 1, and for this, L equals to 3. And now we can use this operator size. So the operator size here, defined here, is the expectation of the number which are of the number of the polystring which are not identity. And for the quantum neural network, the expectation value of the operator is after the neural network is this U diagram U. The information of the quantum neural network are all encoded into this unitary. So we can calculate the operator size of this operator. Okay. And here we consider these 5 different quantum neural network structures. And firstly, consider this 8-qubit system. And here we only consider about the 2-qubit gate. 2-qubit gate, and for each gate, just coupled the nearest neighbor. And these 3 are the quantum neural network structures in one-dimensional system. And this is a popular brick wall structure, which looks like the real brick wall structure. And this is the chain structure where the qubits are coupled one by one. And this is a lambda structure. We also consider about the 2-dimensional quantum neural network structure where the qubits are set at a circle, and a 3-dimensional structure where qubits are set at the vertices of a cube. And for these different neural network structures, even the 2-qubit gate number the same, the information scrambling ability is also, but the information scramblability is different. Before we proposed the quantity operator size to characterize the information scramblability for a specific operator. But here we care more about the structure, not the parameters. So here we take the high random average of each 2-qubit gate. So this, and we define the size bar as the average operator size to characterize the information scramblability of a neural network structure. After the average, the size bar is just depends on the structures of a a neural network. And here, this figure shows the analytical result of the operator size of these 5 different structures. We can see that for the brick wall structure, which is the most popular one, but the average operator size is the smallest. Then is the chain structure, the lambda structure, hyperbolic, and the supercube structure is the largest one, which means that the information scrambling ability is the most powerful.
Hey,
So,
sorry, can I interrupt? There is a question in the chat. Nico, I think asks whether, can you explain more how you take the integral over unitarities?
You mean take the integral over or unitaries? I see. So the integral means that here for each 2-qubit gate, we take the random average of each 2-qubit gate. So and for the different structures, for different neural network, they are all built by this 2-qubit gate. So we just take the random average of this 2-qubit gate.
Okay, there is another question also in the chat, so I can also read it to you if it's. Oh, okay, it's tough to read. Okay, can you maybe check that?
Here we sorry. This one. For the structure, here we just we just care about the single qubit measurement. So for the radar qubit, we measure its poly sigma x, but for the other qubit, just see them as the identity. So this is the measurement operator of this quantum neural network. But after the evaluation, we take the average of this operator, and the U is the content. The U contains the information of the neural network, where the 2-qubit gate, the parameters of your 2-qubit gate, and the structure of the neural network are all contained at this U. So is that clear?
Well, more or less. I don't know. Can you hear me?
Yeah. Yes.
Yeah, I was just wondering. I get what this pedicis x stays for in the sigma hat in the top left equation. Is this like a transformation which has been applied? Because I mean, the sigma, the upper pedicis, like the 1 to n.
The subscribe is the number of qubits. For example, for this 8-qubit system, the n equals to 8.
Yes, exactly. So the upper.
The R means the readout qubits.
Right, and the pedicis, what does it mean? Sorry, I just maybe didn't get that.
So you mean this one? 0 means identity, and X means the sigma X. So
okay. So basically, this means that it has been like an X matrix is a Pauli X operator has been applied to qubit R.
Yeah. So this is the single qubit measurement, which means that just apply the sigma X at the radar qubit, and for the other qubits are all identity.
Okay. So this depends on the unitary that is applied at each step of the circuit.
Yeah. So the information of the neural network are all contained at this U.
Okay, I see. All right. Thank you.
There's another question from Nikos on the chat, but I think, Nikos, you may just unmute yourself and talk. It's easier for the speaker.
So
can you hear me?
Yes,
okay,
perfect.
okay.
Yeah, thank you. So I'm a little confused. I'm not sure how mathematically is defined the integral over unitaries. Do you sum over different unitary matrices? How do you perform it mathematically? If I want to write down, for example, and compute it myself, how would I do it?
Sorry, can you see that again? Sorry, I'm not very clear about your question.
At the size, when you define the size, the average size, you integrate over this du, right? The unitary metric. So how do you define it? Do you sum over different unitary matrices, like unitary 1 plus unitary 2 plus unitary 3, or?
No. Here the integral of u means that we want to so the meaning of this one is we take the average of this okay. For the neural network, there are two properties. One is the structure and the other is the parameters, right? And here the integral means that we take the average of the parameters for each 2-qubit gate. So
okay.
So this quantity just depends on the structure and independent on the parameters.
Okay, so it's summing over the parameters. Okay, thank you.
Yeah. Okay, so should I go on?
Yes, please. Perfect.
Okay. And now this figure shows the different structures have the size is also different, means that the information scrambling ability is also different. But before we mentioned that the different structure, maybe the learning efficiency is also different. So we propose that for the structure which the information scrambling ability is more powerful, maybe while you apply them to the machine learning tasks is more efficient. Okay, and now we use two machine learning tasks to verify this conjecture. First is a quantum information recovery task. Here we have a set of product state size 0, and we have the label of this. The label is the total magnetization of these different product states, and then unfortunately these wave functions are evaluated by a very chaotic Hamiltonian edge during a long enough time. So we want to use the quantum neural network to extract the total magnetization of this product state from this wave function, which are very high entangled. And here we train these 5 different neural network structure with the same training data set, and to avoid the accidental error of the initialization, we take 10 times initialize to train the different structures. And the curve is the mean value of the loss, and the shade is the variance of the loss. So from the right figure, we can see that during training, the brick wall structure, the loss decreased the slowest, and then almost the chain structure lambda hyperbolic, and the yellow one, which means the supercube structure, decreases the farthest. So from this, we can see that while the information scrambling ability is more powerful, the learning efficiency is also while during learning, the structure is more efficient. And we also saw the similar phenomena from the classical pattern recognition task. Here we use this quantum neural network to classify this street view of house number images. First, we encode this free channel RGB figure to quantum wave function, and the measurement, the sign of the measurement represents two different classes. For the positive sign represents the number 9, and the negative sign represents the number 6. Similarly, we can see that during training, the accuracy grows the farthest is the yellow one. So, and then is hyperbolic, the lambda structure, the brick wall structure grows the slowest. So, from these two tasks, we can see that the learning efficiency have the positive relation of the information scrambling ability of the quantum neural network. Okay. To summarize, in this work, we propose a scrambling ability defined by the average operator size, and this average operator size is positively correlated with the learning efficiency. And from these two machine learning tasks, we verified this conjecture. And this work is with the help of my advisor, Professor Hui Zhai at the Tsinghua University, and Dr. Pengfei Zhang at the Caltech. And here is the e-print of this work. So thank you. Thank you very much.
Thanks a lot. So thanks a lot for this interesting talk. Do you have, oh, there are some questions. Give me a second.
So thanks for the talk, first of all. You compare different circuit architectures and yeah, basically calculate this average operator size growth. Do you have any intuition on why certain circuits perform better?
So you mean why we propose the positive correlation between the learning efficiency and the information scrambling ability?
No. They're more like if you want to now design a circuit which like optimizes the size growth, how would you approach this task?
Sorry. Okay.
Yeah, like if I want to now to design a circuit which like gets this higher performance or the higher accuracies, you would need to find a circuit which maximizes your average operator size growth. Do you have any intuition how or what makes the circuit suitable for this task?
Sorry, you mean how why we choose this one?
Yeah, and what makes different architectures better than others?
So this first, I think intuitively, because the high dimensional system, the qubits can couple to one qubit can couple to each other more more closely. So maybe with the dimension is higher, the information scrambling ability is also powerful. Because you can see that for the one-dimensional system, the qubit can just couple to the nearest neighbor, the 2 qubits. But for this cube structure, it can couple to another qubit, which are while translate it into the one-dimensional, it can couple to the qubits which is far from it. So maybe this one is more, powerful.
Okay, so thank you. Maybe the conclusion to draw is that better interconnectivity is just better in performance, right? Okay, thank you.
Okay.
And there's a question in the chat by Tianfeng, so I can read it for you. So that's quantum neural network with greater information scrambling ability perform better in VQE. I guess it's a variation quantum eigen problem, right? So, but you can, Tianfeng, you can also unmute.
Okay. Can you hear me?
Oh, okay. Yeah.
Oh, yeah. Thanks for your interesting talk. I want to know, have you tried the variational quantum eigensolver with these models? Maybe the circuit with better information scrambling ability will perform better. I'm not sure. Have you tried?
No, I have not tried.
Oh, since as far as I know, in VQE, okay, for some Hamiltonians, we need a special kind of circuit. For others, we need different. So is it possible that in quantum machine learning, for some tasks, we need this circuit with this structure, but for another one, we need another one? Is it possible, do you think?
Yeah, I think it's possible because just like the classical neural network for different, while you apply the machine learning model to the to solve a problem, is the algorithm always, I think generally algorithm always depends on the problem what you want to solve, right? So because if you want to do the classification, maybe convolutional neural network is better. While you want to solve some problem, we have the time sequence. Maybe the recurrent neural network is better. So similarly for the quantum neural network, for different tasks, the different structure, the different structure have different learning efficiency. But here we just propose general. While you want to use to solve the regression problem, while you want to solve this supervised problem, because let's back to this two extreme example. For this task, for this kind of structure, we can say that it's bad. It's not good for any machine learning tasks, right? So we just propose a general idea. While you build quantum neural network structure to solve a problem, maybe the information scrambling ability is also a quantity you need to consider about while you build the neural network.
Okay, thank you.
Okay, great. So maybe we can take one last question. Okay, one last question.
Okay.
Can you go back to the slides where you show these different structures?
Different structure, okay. This one?
Yes. So it seems like for the supercube, you have more gates. So did you ensure that you have the same number of gates for each architecture? Because otherwise, I think it's not a fair comparison.
Here I just showed a unit of a structure, and for here, because the number of units means we coupled the unit. Means we repeat this called a one unit, and for the units. For the units, for example, this 4, we repeated this structure 4 times. But for this structure, the gate number is the gate is we also repeat 4 times. But the total qubit gate fixed same as this one. For example, this one each unit contains 7 qubit, right? 7 gates. So for units, while units equal to 4, the total number of the 2 qubit gates is 28. And for this structure, we also repeated 4 times and choose first 28 2 qubit gates.
So I mean, like 4 units of the supercube have the same number of gates as 4 units of the brick wall. Is that correct?
Yeah.
Okay, thank you.
Okay, then let's thank again the speaker. Thanks a lot.
Okay, thank you very much.